Welcome back to the Harvest Fest, ECE 220. We were harvesting things before class started. Hint, hint on your extra credit, maybe. Group A, we have one more section, Section H. Your lab is this afternoon. I will see you there, hopefully. Group B, your pre-lab for lab number 2 is due Saturday. You should have already read Chapter 5. Now be reading Chapter 6. We will start Chapter 6 material on Monday. And if you're needing to apply for advanced standing, you have a couple of weeks remaining to do that. Homework 7 is due on Tuesday, as is or will be Group B, Section I. You'll have your lab on Tuesday of next week. That's lab number 2. Group A, your lab number 2 reports will be due the following day on Wednesday, and then everyone will get to come together and sing for the exam. Exam number 2 is next Thursday. And that will be covering Chapter 4. Homeworks 4, 5, and 6. Today, what I want to do is look at various op-amp circuits. We're going to solve some problems. We're going to do some exercises today. Looking at various variables in op-amp circuits, we'll then actually go back to where we started, sort of finished last lecture, which was looking at what do these op-amp circuits look like from the output side or at the output terminals? What are their Thevenin equivalents? Can we find those? And hopefully we will get eventually to this realistic op-amp model. You already have the Chapter 4 material to be able to analyze that. It's just a little bit more nodal analysis. We've been breezing through the electrical analysis with these op-amp circuits because we're assuming ideal op-amp conditions or assumptions. If we don't impose those, if we say, well, let's get closer to reality, the analysis gets a little more involved, but the results are about the same. That's the bottom line. If we don't get there, maybe I will get there after class if we don't get there during class. Let's do some exercising. Let's find different variables in various circuits. Here's example 1. And these will be interconnected maybe a little differently than the traditional op-amps. We've talked about inverting op-amps, non-inverting op-amps, the difference amp, the buffer. The buffer goes with the non-inverting amp. But here is an op-amp circuit that we're now driving one of the input pins with a current source, an independent current source. And we are now asking the question, what is the output current going through that load resistor? The load resistor is 5K, and that's what we're trying to find, is that current I sub L. Now that you have that circuit drawn and you're visualizing it, you should be dreaming op-amps. When you lift your head up off the pillow, you go, oh, that was a non-inverting. You might be dreaming of this stuff, but you'll be dreaming triangles. You've been dreaming circles and resistors and diamonds so far. Now we introduced a new shape, a triangle. It has, and what's missing here that's implicitly assumed from this circuit? What is missing? And now you might ask, will it actually function? That's what I'm asking behind that first question. Will this even move or do anything? Given the way I've drawn it here, what I am not drawing explicitly are the power supplies, the rails that are supplying this. So you would have to energize this with a voltage at the positive supply pin and a voltage at the negative supply pin, and that negative supply pin could be, it just needs to be less than the positive supply pin. It could be grounded, or our reference node. It could be just less than, but traditionally it's less, 0 or lower. But here is our circuit. Now, and what's another key thing to keep in mind when you're solving these on the exam or in homework? Whether we're viewing this op amp as we've typically done it, or are we looking at it in a mirror? Has it been flipped? Have we inverted? Is it standing sort of on its head relative to how we've been seeing it? Here, now pay attention, the positive, the non-inverting terminal, input terminal is on the top. So if you're now looking for this feedback path, where do you want to find it? It now needs to be going from the output pin back to the inverting input pin, which it is. So here we do have negative feedback, and we're assuming ideal op amp. The NFB, National Football Bowling League, I don't know what it is. NFB, the negative feedback, allows us to assume what? What is that good for? Why do we care that we have negative feedback? What did we say that helps us do in our analysis? Or what does that force upon this circuit that we're going to assume during the analysis? That says we have this virtual short between the input pins, or that the positive or the non-inverting pin voltage and the inverting pin voltage are the same. Now what do we do? With the football thinking, we don't want to drop back and punt. We want to keep going down the field. Whatever that means. We said we were exercising, right? Need to loosen up. What do we need? Or what can we say now? Can we say anything more? It looks too different from what I'm used to. Well, let's just start thinking through this. Do we have anything happening here? What's I sub n? Pardon? 0. The resistance is really big going into the op amp, so this current is 0. What about this current? That's 0 as well. So all of this current from that current source is going through the 5K resistor that's in parallel with that current source. And what does that allow us to do? Now we're going really far back into the textbook. Now we're just applying Ohm's law. Now we can find this voltage, and what is that voltage? Could we label it with a familiar label? We could say V sub 5. You won't find V5 on the grocery shelf. We looked and found V8, didn't we? I've heard that humor helps us learn, so bear with me. Putting us in a good mood helps our brain actually remember and think. Puts us in a more welcoming role for processing. It's V sub 5, or it's also what? What's this node or this node? They're all the same. Isn't that the non-inverting pin? This voltage is the voltage across that non-inverting input pin, or that's the voltage at the non-inverting input pin. What is V sub P? Ohm's law. We have R times I. The M and the K, they cancel. We had 10 to the third and 10 to the minus 3. So now we have 10 volts at V sub P. And because of negative feedback, we now know that that is also V sub N, which V sub N is right here, isn't it? And how is V sub N now? We need to find V sub O to find I sub L. How is V sub N? Can we find the current through that 10K feedback resistor? It's 0, isn't it? There's no voltage drop across that 10K feedback resistor, which now says since I sub N is equal to 0, we now know that V sub N is actually the same as V sub O. And we just calculated V sub N, which was V sub P. That's 10 volts. Now, Ohm's law again will allow us to find I sub L. I sub L is V sub 0 over 5K. Or I sub L is now 2 times 10 to the minus 3 amps, or 2 milliamps. That's I sub L. That was kind of fun, wasn't it? I guess it's all relative what you think fun is, but hey, you're an electrical and computer engineer. This is fun. All right, let's go on. Let's have some more fun. Example number 2. Find V sub L. Wow, these circuits are looking kind of strange, but you can analyze them. You can just apply your steps and work through and figure it out. And if you like to start at the answer and work your way back, what's another way of thinking about this problem? If you wanted to find V sub L, do you see that that could be found if we knew this voltage? What I'm not showing is that's all the same node, and that's our common node. If I knew V sub O, if I knew the output voltage, could I now find V sub L? That's a voltage divider, isn't it? V sub L is a ratio away from V sub O. And because of the resistors, it's actually half of V sub O. So if we can find V sub O, and now what have I done with the op amp? I've flipped it again. Now the inverting input pin is on top, the non-inverting pin is up or below. And do I have negative feedback? Yeah, I have it directly connected, even no resistance. I do have negative feedback. And that allows us to assume. Why am I saying assume that? Because at the very end, we're going to have to check to see if that output that we obtained is in fact within the rails, the supply rails. And I haven't even indicated the rails, so let's just assume they're very big. I haven't drawn them on. I haven't even given you those values. So let's just assume we're not going to be in saturation. And you could write that on your multiple choice exam. You could, and then you could argue with me when you didn't get the right answer on that one, if it did involve saturation or not. You're assuming no saturation. Now what? What else do we know? Do we know anything about this? That's 0 if it really matters. But that kind of gets us thinking, maybe. What's this? That's 0. Which now allows us to say that all of that current, that 5 microamps, is going through that 100K, and that will now allow us to find V sub P. We're trying to find V sub L. What's V sub P? That's now Ohm's law. That's 100K times 5 micro. So now we have a little bit different. We need to keep track of the K and the mu. We have 500 M. K times mu is M. You learned that in algebra, right? Or not funny. Okay, so we have 500 millivolts, or 0.5 volts. That's now V sub P. Does that help us, knowing V sub P? Are we just spinning our wheels? We know we have negative feedback, so that means V sub P is the same as V sub N. And what's V sub N? V naught. That's the output voltage. It's the same. It's wired. It's at the same potential. So now we're getting somewhere. We know that V sub P is equal to V sub N by negative feedback. V sub N is equal to V sub O because it's connected with the wire. R sub F in this case is 0. And we just computed that to be 0.5 volts. What's V sub L? So what you don't want to do is just quickly go, oh great, I found the answer. It's 0.5. Let's bubble that one. Remember? V sub L is a fraction of V sub O. So one of the answers might be 0.5, and you'll get all excited because you see it, you bubble it, and then you move on and you go, oh, sorry, really? Yeah, unfortunately. So V sub L is now a voltage divider away from V sub O, and this is now 1K over 1K plus 1K V sub O. Or we now have 1/2 of 1/2, or 0.25 volts. Stunned silence. So we'll move on. Let's put some lights on this exercise activity. Let's see if we can turn some lights on. Let's see if we can illuminate some LEDs. That's example 3. Now we're asking which LEDs are in fact on. And we're going to have two conditions. We're going to have V sub S being bigger than 5 and V sub S being less than 5. But right now we just kind of want to get our head around this circuit. And what in the world, what are all the wires and what are they doing? Here, I'm actually showing you the rails, the power supply rails. I'm showing you that the positive voltage power supply is what value? 15 volts. What's the negative supply value? 0. It's our common. We have V sub n, V sub little n is 5 volts, V sub p is V sub s. Do we have negative feedback? Now what you don't want to get too forgetful of is, wait a minute, the way he's drawn this, that op amp really only has things going to the input pins and things going to the supply pins, nothing connecting the output of the op amp back to any of the input pins. There is no feedback here. Let me change color so it stands out. What does that mean? If we have no feedback, now we've always had feedback, which means we were working in a closed loop, so to speak, environment. Now we are not. Now we're doing open loop. And what do we know if we're in open loop? What is the output? We need to kind of find or keep track of. And that's kind of confusing, is it not? The way I've labeled that, do you see how that could... I'm meaning from the output pin to here. I'm not saying the voltage from the negative supply rail. Is that... V0 is the voltage at the output pin. We would like to know what that is. What is V0? What's the relationship between V0 if we don't have any feedback? What is V0 in an op amp? What's it related to? Now be thinking about one of the first figures with this operating region where we had the linear operating region and we had the saturation on the low side and the high side. What was the linear operating region functional form? What was the horizontal axis in that figure? That was the difference between the non-inverting voltage on the input pin and the inverting input pin's voltage. V sub p minus V sub n. V sub O, or the output voltage, was A, V sub p minus V sub n. And A is huge. Bigger than 10,000. Which means that if V sub p is a little bigger than V sub n, V sub O is going to... If V sub p is bigger than V sub n, what happens to the output voltage? If you just applied this functional formula, You would say, oh, it's 10 to the 5th times whatever that voltage difference was. Yes? I'm sorry, I can't hear. What? Yes, so now we're going to be in saturation, aren't we? We are going to saturate in this environment. It's going to be going either plus positive rail or lower supply rail. We're going to be bouncing between that depending on the relationship between the voltage on those input pins. In this case, if V sub S is bigger than 5 volts, this is in fact V sub P, this is V sub N. If V sub P is bigger than V sub N, this is now positive. This is going to be positive, which means that V sub O is going to be in saturation, and it's at the positive value, the high side of the rail. If this is now 15 volts, can you tell me which LED is on and which LED is off? I didn't expect to be, so here, let me just say here's LEDs, and here's their status. Here's the top one, and there's the bottom one, and their status is either on or off. Is the top LED on in this part A? No, we have no voltage drop across the pins of that LED. There's no potential to drive current through that LED. It's off. The top LED is off. What about the bottom LED? We're hoping maybe these are LEDs are poor choice because now we're driving it with 15 volts. We'd want to put a resistor in there, or we wouldn't see this on for very long. So poor design, but let's say these are really well or very forgiving LEDs. So this one is now off, and that's on. What about the next case? Whoa, where did I go? Oh, we were going back to another day and time. Let's now get rid of that. And now we have V sub S less than 5. What's V sub O going to be now? It's now going to be at the negative supply rail, which is 0. Now we have V sub O being 0 volts. Now we can draw our LEDs and their status. If that node between the two LEDs is now at 0, is the top LED on? You know what? How do I draw a lamp? But that's a lamp. You guys can take a nap if you want. I'm just correcting some things here. Sleep is good for learning as well. Oh, I shouldn't have said that, should I? Now everybody's taking a nap and they're going to say, well, I was just learning. Okay, as long as the president doesn't come in here and see this class with everybody's head on the lap. We're recording. Stop. All right, we have some lamps here. Let's get back to class. What do we have? Top one is now on, bottom one is off. We good with this example? Now I have to remember what I just said. Off. That's not what I said. Somebody's asleep at the wheel. All right, let's move on. Example 4. Find V sub t. And V sub t is now across a resistor that's somewhere in this circuit. If that V sub t was not there, would you feel a little bit more comfortable? I'm sorry, if that resistor with which V sub t is being measured, if that resistor was removed, would you feel a little bit more comfortable with this circuit? Yeah, then it would be our traditional inverting op amp configuration. Now we've put a little bit of a wrinkle on that, and we now need to find V sub t. But we go, okay, let's see, this is, can we analyze this with the strategy or the steps that we've learned? Is there negative feedback? Yes, you are feeding information back from the output pin to the inverting input pin. We do have negative feedback. And that now allows us to assume V sub p, which is right here, and V sub n, which is right there, are virtually connected. There's a virtual short there. They're the same potential because of the negative feedback. What is V sub p? Value-wise. That's our reference node. V sub n is now nothing. What's the next step traditionally in our analysis approach? First, we check for feedback. It's negative. Good. That allows us to assume V sub p is equal to V sub n. Now, we typically look at KCL at the inverting input pin. Let's do KCL at V sub n. And I'm going to keep V sub n in there so that you know what I'm trying to say. We now have V sub n minus V sub s over 4.8k plus V sub n minus, let's just go to V sub t, and now what's the current? Now I'm trying to find that current going up vertically out of that node. I now need to divide by 30k. That's the resistance between those two nodes. And then I have I sub n going into the op amp, which is 0. But what did we just conclude? What did we say? We said that this can actually be simplified a little bit. We had basically three variables. V sub s is assumed given or known. V sub n was floating around, but now we are using the fact that we have negative feedback and V sub p was 0. That can go away. Now we can write V sub t in terms of V sub s. V sub t over 30k is now equal to minus V sub s over 4.8k. Or V sub t is now minus 30k over 4.8k times V sub s. And that actually ends up being, if you divide 4.8 into 30, that's going to give us 6.25 as a scaling factor or as an amplification on V sub s. And if we weren't told what V sub s is, this is as far as we could go. We would just say, oh, V sub t is now minus 6.25 V sub s. That would be our answer. We were asking to find V sub t. But sometimes we want to do a little extra. Let's do a little extra in this case. And let's just keep going. Let's see if we can find a relationship between V sub s and V sub o. Can we? Why don't we just find another KCL or write another KCL equation at the output? Or I'm sorry, at V sub t. V sub t is sort of this intermediate node. Let's now write KCL there. So now KCL at V sub t allows us to say that V sub t minus V sub n over 30 plus V sub t over 1k plus V sub t minus V sub 0 over 30k. And again, we know that this is 0. Or we now have 1 over 30k plus 1 over 1k plus 1 over 30k. Those are all being used to scale V sub t. And let's put V sub 0 on the other side. If we now multiplied both sides by 30k, we now know that V sub 0, I'm switching sides on V sub 0 and V sub t, that's now 1 plus 30 plus 1, or that's now 32. V sub t. And we just had a formula for V sub t in terms of V sub s, which allows us now to conclude that V sub 0 is 32 V sub t, but that's 32 times minus 6.25 V sub s. So this now, if you multiply 32 times 6.25, you end up with V sub 0 being a pretty big multiplier relative to V sub s, the input voltage. So now you've amplified your gain by putting that little T network in the feedback path. And it didn't take too much to solve it because V sub p was 0 and we were good to go. That last part was extra versus what we were asked to find, which was V sub t. And if on the exam they gave you a V sub s equaling 1, you would then say, oh, V sub t is minus 6.25. Bubble that one in. can we just start adding these pieces together? We have different puzzle pieces, different op-amp circuits. Now we can actually cascade them or combine them. Now we're putting two op-amp circuits in cascade or together, back to back. And now we might be interested in what's the overall gain between the input V sub S and the output V sub 0. If you were just looking here, can you relate V sub 1 to V sub S? You have negative feedback in both. We'll assume we have linear operation. What's the gain here? Or what's the relationship between V1 and V sub S? Isn't this just the standard inverting op-amp configuration with R sub F being 1K and R sub S being 1K? This is now minus 1 V sub S. So the gain here is minus 1. What about this sub-circuit? What's the gain there? Now we're looking for V sub 0 in terms of V sub 1. That's an exact duplication of the left sub-circuit. That looks exactly the same. This gain is minus 1. Here's a minus 1 V1. And now do you see that overall we now just have, V sub 0 is now minus 1 V sub 1, which is minus 1 times minus 1 V sub S. And now we've used this cascade combination to change the signs back, and just because of the way we selected those resistors, we're just seeing the same voltage at the output pin as we see at the input pin. And you could vary that up by switching the feedback resistors, the input resistors, etc. Which, if you didn't want to invert your gain using an inverting, but you wanted to scale it, do you see you could cascade a couple of these together? You still have to worry about saturation, but now you can start interconnecting these, and that's how you could actually change these difference amplifiers into a better performing circuit like an instrumentation amplifier, which you can get to later after the final. Oh, that was a welcome relief, huh? Let's now look at Thevenin equivalence at the output terminals. And we've already seen this one. This is what we finished the class with last time. What did we say was going on here? Now we want to find what does, if I wanted to replace this that I've now encircled with this dashed border, I want to find the Thevenin equivalent that's inside that dashed boundary. I want to find what's going on. I really just want to collapse all of that into a Thevenin equivalent between terminals A and B. And we had a couple of methods for doing this. Let's just go the direct route. I think that we called that method 1. let's find, so here was step 1. This is a review for next week's exam. This we found V Thevenin. Then we interconnected the circuit a little differently, and in step 2 we find I short circuit. But V Thevenin is just going to be the output voltage with nothing connected to the output. Can we analyze that? And that's now a very traditional, do we have negative feedback? Here's V sub P, that's sitting at 0, so now we know V sub N is 0. And now we could write KCL at that inverting pin if we needed to. Or if you remembered the formula, you could write that down and proceed. But here we have V sub N minus V sub G over 2K plus V sub N minus V sub 0 over 180K plus no current going into the op amp equaling 0. V sub N was 0. Now we've just re-derived the formula for the inverting amplifier. Or V sub 0 is now minus 90 V sub G. And this is our V Thevenin. What about I short circuit? Now if we go back here and we actually short pins A and B, terminals A and B, and measure the current, now we're assuming an ideal amplifier or an ideal op amp. So now in this particular case, in fact, if we shorted the output terminals for an ideal op amp, we can get as much current as we want out of that, is the ideal scenario. We're not assuming the real data sheet limits on that current. So if that's the case, if we just now had that allowed to do whatever it wants, it's just going to go to infinity. We're going to have an unlimited amount of current flowing out of that op amp in the ideal scenario. Now we can do step 3, which is to find R Thevenin, which is V Thevenin over I short circuit. And in the limit, as I short circuit goes to infinity, this becomes 0. So that now our Thevenin equivalent between terminals A and B is now minus 90 V sub G and no resistor. The internal impedance, and this is now an ideal voltage source. Is what that op amp looks like. Now, after class, I will go ahead and continue and show that we get something similar here for the non-inverting amplifier. It now looks like an ideal voltage source. And maybe I will go ahead and do the realistic or more realistic op amp expressions, and you can look at those, and you can look at the last section of chapter 5 and read through that. We'll start with chapter 6 next week.